Section 4.4. Sketch the graph of a function accurately by hand. This section 4.4 essentially is a review section. You need to apply what you have learned so far to sketch the graph of a function. The following is a guideline of sketching the graph of a function by hand. If you follow the steps in the guideline to sketch the graph of the function, then the curve that you obtain is accurate, almost no different from the graph plotted by a graphing calculator. Step 1. Determine the domain of the function. Why? Because outside the domain, the function has no graph. Only within the domain, the function has a graph. So, step 1, determine the domain of the function. Step 2, symmetry. There are two types of symmetry that we often consider. One is even function. Even function. What it means, even function? When the graph of the function is symmetry about y-axis, for example, this case, then the function is called an even function. If a function is an even function, then our work to sketch its graph can be cut in half, because we just need to focus on sketch the graph of the function on the right half plane. After we get the graph of the function on the right half plane, we can reflect this portion about y-axis to the left half plane to complete the whole graph. So our work can be cut in half. We just need to focus on the sketch on the right half plane. Then, how to know a function is an even function? Have a check with this equation. When this equation is true for any x, then the function is even function. The second type of symmetry that we often consider is off function. Off function. What is an off function? When the graph of the function is symmetry about the origin, then the function is an off function. Here is one example. The graph is symmetry about the origin. That means that you can rotate, for example, this portion of the graph 180 degrees about the origin to get the other portion of the graph of the function. When a function is an off function, again, our work can be cut in half. We just need to focus on the sketch on the right half plane. After we get the portion on the right half plane, we rotate this portion about the origin 180 degrees to complete the whole graph of the function f. To know whether or not a function is an off function, have a check with this equation. If this equation is true for all x, then the function is an off function. Step 3, determine where the function is increasing and where it is decreasing. After we get increasing, decreasing information, then we can determine local maximum, local minimum. Step number 5, determine where the function is concave up, where it is concave down. Then determine points of inflection. These 3 steps, we learned them in the last section, 4.3. Step number 6, find asymptotes. To find horizontal asymptotes, compute limits at infinity. For example, if x approaches positive infinity, function approaches some finite number, then that number is a horizontal asymptote. Similarly, if x approaches negative infinity, function approaches a finite number, then the finite number also is a horizontal asymptote. So horizontal asymptotes are about m behaviors of the function, of the graph of the function. To find vertical asymptotes, first, find points where denominator is 0. Vertical asymptotes. A vertical asymptote can only appear at a point where denominator is 0. After you get the point, compute left-hand limit at the point, right-hand limit at the point. If one of these 2 limits is infinity, then the point is a vertical asymptote. Step 7, determine x-intercept, y-intercept. That means that determine where the graph of the function gets across x-axis and y-axis. To find x-intercept, set y to 0 and solve the equation f of x equals 0. Solve this equation for x. Then the x is x-intercept. To find y-intercept, set x to 0. That is, compute function value at 0. Then the function value at 0 is y-intercept. After we connect all the information, then step 8, sketch the graph of the function. Let me show you one example about these 8 steps. Example, use the guideline to sketch the graph of this function. This function is complicated. To compute its derivatives, you need to apply quotient rule. Then when you compute derivative on square root of x plus 1, you need to apply chain rule. Because the computation of derivatives is difficult, this example directly provides us first derivative and second derivative. So we don't need to compute the derivatives of this function ourselves. Okay, now let me follow the guideline to sketch the graph of this function. Step 1, determine domain. The domain of a function is the set of x values where the function is computable. Let me try some numbers. Say try -2 for x. When I plug in -2 in x, denominator is square root of -2 plus 1, not computable. So -2 is not in the domain. How about -1? If you plug in -1 in x, then denominator is square root of -1 plus 1. It is 0. So the function is not computable at -1. Then how about try -0.5? Now computable. So any number greater than -1, the function is computable. Therefore, the domain is this interval. This interval. The function f has graph only on this interval. Because this interval is not symmetric about 0, the origin, not symmetric about the 0. So the function has low symmetry. An even function, its domain must be symmetric about 0. An odd function, its domain must be symmetric about 0. Because the domain of this function is not symmetric about 0, so the function must be not an even function, not an odd function. So low symmetry, then we can exploit about this function. Now step 3. Determine intervals of increasing, decreasing. We just learned this topic in the last section, 4.3. To find intervals of increasing, decreasing, I suggest 5 points where derivative is 0 or doesn't exist. Why? Because I want to use these points to cut the domain into intervals, into subintervals. Okay, now let me find the points where derivative doesn't exist first. Derivative is here. Clearly, when x is -1, denominator is 0. There, derivative doesn't exist. So at -1, derivative doesn't exist. But -1 is outside the domain. So ignore it. I don't need to consider -1. Outside the domain, low graph. So just ignore -1. Only at -1, derivative doesn't exist. Now, 5 points where derivative is 0. Set derivative to 0. Set this guy to 0. Yeah. Then move denominator to the right side to get this equation. Then we have 2 points, 0 and -4/3. At these 2 points, derivative is 0. Again, -4/3 is outside the domain, So I ignore this point. Therefore, only 1 point where derivative, only 1 point inside the domain where derivative is 0 or doesn't exist. The point is 0. Now, I use this point to cut the domain into 2 subintervals here. This is an x-axis. The domain is from -1 to infinity. Now I use 0 to cut the domain. Then we get 2 subintervals. Now let me determine increasing, decreasing on these 2 intervals. How to determine increasing, decreasing? Remember, consider derivative. If derivative greater than 0, increasing, less than 0, decreasing. In this interval, I arbitrarily pick a point, say, pick negative 0.5, and then plug in negative 0.5 into derivative. Plug in negative 0.5 here. Then I get negative 1.77 less than 0. That is over this interval, derivative less than 0. So the function f is decreasing. The graph is decreasing. On this interval, I pick a point, arbitrarily pick, say pick 1. Plug in 1 in x here. Then to get this number, positive. On this interval, derivative is positive. Therefore, the graph of f is increasing. This is a step 3. Now, step 4. After we have increasing, decreasing information, then we can tell local maximum, local minimum. Here, I roughly sketch the graph of the function f. Not accurately. This sketch is just for answering this question. Local maximum, local minimum. Okay. Now, here, negative 1 to 0, the graph decreasing. Then 0 to infinity, increasing. So the graph, the function has a local minimum at 0. The local minimum function value is function value at 0. Function, yeah, here. Plug in 0 in x, then function value at 0 is 0. So 0 is a local minimum function value. Local maximum. Now, step 5. Determine intervals of concave arm and concave thumb. Now, concave arm and concave thumb, you need to consider second derivative. To find intervals, first, find points where second derivative is 0 or doesn't exist. Second derivative is here, we are given here. The points that make second derivative doesn't exist is negative 1, because when x is negative 1, denominator is 0, doesn't exist. Yeah. So at negative 1, second derivative doesn't exist. However, negative 1 is outside the domain, so ignore it. Okay, now 5 points where second derivative is 0. Set second derivative to 0. Okay, yeah. Set this guy to 0. Yeah. Then solve this equation. Move denominator to the right to get this. Now to find solution of this equation, I use quadratic formula. Negative b plus minus square root of b squared minus 4ac, then over 2a. Then I get this number. Square root of negative number, it is a complex number. In calculus 1, actually, cal 1 to cal 3, we only consider real numbers. So that means that low x, where second derivative is 0. Okay, now low point I can use to cut the domain. Okay, so low point, so only one interval. Now let me determine the sign of second derivative on this interval. Arbitrarily pick a point, say pick 0 and evaluate second derivative at 0. Yeah, second derivative. Now I plug in 0 in x, plug in 0 in x. I get 2 positive. Oh, on this interval, second derivative positive. So the function, the graph of the original function is concave up. Second derivative greater than 0, it is concave up. Less than 0, concave down. So concave up. So from -1 to infinity, the whole domain, the curve, concave up. Therefore, low point of inflection. A point of inflection is a point. There, the graph changes concavity. Low point of inflection. Continue with this example. Step number 6. Find horizontal asymptotes and vertical asymptotes. To find a horizontal asymptote, you need to compute a limit at infinity or a limit at negative infinity. Because the domain is from -1 to infinity, x independent variable cannot approach negative infinity. So we don't need to compute limit at negative infinity. Now we just need to compute limit at positive infinity. Compute this limit. How to compute this limit? You can use a table. So table, easy to get, the limit is infinity. If you don't want to use a table, you can use analytical method. Say, take out the highest degree term from the numerator and from the denominator. Or you can use L'Hopital's rule, right? You can use L'Hopital's rule. L'Hopital's rule is in some previous section. I don't remember the section number. About this limit, actually, you can get the limit by inspection. The numerator, the degree is 2, right? X to 2, the degree is 2. Denominator, the degree is 1/2. So when x approaches infinity, numerator approaches infinity much faster than the denominator, the approaching infinity. So the ratio should be infinity by inspection. Because infinity is not a finite number, therefore the function, the graph of the function f has low horizontal asymptote. Okay, now let's find vertical asymptote. A vertical asymptote can only appear at a point where denominator is 0, because only when denominator is 0, function value is likely to be infinity. Okay, now I set denominator of the function to 0. Okay, I miss 0. Square root of x plus 1 equal to 0. I miss 0 here. Take square on the both sides, then I get this equation. So I get -1. So at -1, denominator is 0. Now let me consider, so at -1, the function is likely to be infinity. Now let me consider the limit at -1. Left-hand side limit is impossible because x, left-hand side, x approaches -1 from the left side. X is outside the domain. low function value. So we don't need to compute left-hand side limit. We just need to compute right-hand side limit. X approaches -1 from the right side. Okay. Now, how to compute this limit? You can use a table, but tedious. Let me use direct substitution. Directly plug in negative 1 in X, then I get 1/0. 1/0 is an infinity, either positive or negative. To determine the sign of this infinity, I pick a point very close to -1, and from the right hand side, say -1 here, a point on the right side and very close to -1. So I choose -0.9. Then compute function value at -0.9. Function value, the function here. Plug in -0.9 in X, I get this number, positive. That means when X is very close to -1 from the right, function value is positive. Therefore, this infinity is a positive infinity. Positive infinity. Okay, now limit is infinity, so -1 is a vertical asymptote. Step number 7. Determine x-intercept and y-intercept. How to get x-intercept? Set the function f equal to 0. This is a f here. Okay, f. Set it equal to 0 and solve the equation, then I get 0. So the graph of the function f gets across x-axis at the origin, 0. To find y-intercept, set x to 0. I miss 0 here. Set x to 0 and compute function value at 0. Function here. Plug in 0 in x, function value at 0 is 0. So the graph of the function gets across y-axis at also at origin, 0. This is a step number 7. Now the last step, after we have all the information, we are ready to sketch the graph. Okay. Draw an xy plane. Mark down the information. Right? From -1 to 0, the graph is decreasing. So mark down it decreasing. 0 to infinity, the graph is increasing. Mark down the information. From -1 to infinity, the whole domain, the graph is concave up. Mark down it. And also the graph at 0, the graph has a local minimum. The local minimum function value is 0. So mark down the point. Okay, now sketch the graph of the function f piece by piece. First, from -1 to 0, the graph is concave up and decreasing. And also, this vertical line is a vertical asymptote. So the graph looks like this. Okay. When x approaches -1 from the right side, the graph should be closer and closer to the vertical line, vertical asymptote. Second piece, 0 to infinity. the graph is increasing and concave up. So the graph look like this, increasing, concave up. If you use a graphing calculator to plot the graph of this function and compare with this graph, you will see they are very close. So when we follow the 8 steps in the guideline to sketch the graph of a function, the graph that we obtained is accurate.